Okay, so today's lesson is 7.2, which is going to be sort of built off of what we did in 7.1. We're still going to be doing Cartesian vectors, meaning writing vectors as their tail comes from the origin of our Cartesian coordinate system, and the tip we can either write as coordinates or we can write the vector in terms of unit vectors I and j. We're going to do the same thing today, but we're going to introduce 3 dimensions. It's not a big jump, so don't worry too much about it. Let me just zoom in here. This is how we're going to draw 3 dimensions, because we're going to be drawing it on a 2-dimensional piece of paper or screen. So we have our x right here. And the x is sort of angled, and this is your y. So those are still at 90 degrees to each other, but you can imagine them having the x sort of coming out of the screen. And your z, which is going to be our other axis, is going straight up. So here's how we're drawing it. Z, y, and x coming out of the screen. Going into the screen would be our negative direction for x. Going to the left is our negative direction for y. And of course going down would be our negative direction for z. And in terms of unit vectors, I is still going to be our unit vector for x, and so it would have the coordinate 1, 0, 0. J would be for y, so 0, 1, 0, and k is going to be our unit vector for the z-axis, which is 0, 0, 1. So in the example below, this is similar to what we did before, but we are going to write these vectors starting with OP using standard unit vectors. So we're going to write an expression for them. So for OP, which has coordinates 2, 1, and negative 3, we're going to write it as 2i minus j, plus j, that's positive 1, and negative 3, so minus 3k. Okay, and for question 2, we can do the opposite. In this case, OP, which is written as I minus 2j, we can write in coordinate form, which would be 1, negative 2, and negative 1. So I want you to take a couple minutes and try the other examples in 1 and 2, and then we'll take them up. So now that we're dealing with 3 dimensions, we can't just talk about lines, because we also have something called a plane. So if you look at our coordinate system, let's look at this one. So here's our x, here's our y, and here's our z. Sure, you can draw a straight line somewhere, but you can also draw a plane. So this plane is what we call the xy plane, and it pretty much encompasses all the points on this plane where the z coordinate would be 0. Now we can actually take that plane and move it up or down to different z coordinates, right? But it would still encompass everything in there, stretching out to infinity. Okay, similar if we have the yz plane, which is this one here, right? And the xz plane here. So just like our xy plane, we have at only one coordinate at z in our example, z equals 0. Right? On the yz plane, we have it at x equals 0, and on the xz plane, we have it at y equals 0. But we can shift them. And later on, I will talk more about planes and how to graph planes, and we'll also look at intersections between lines and planes and so on. So, but right now, it's fine just to understand what a plane actually is. So just like in yesterday's lesson, we can do a couple of other things. One, we can add vectors in R3. R3 just means 3 dimensions. For example, if we had a vector OB, OC, and OD, right, we could add them all. Right? We can say OP is the sum of all 3 of them, in which case, just like when we did 2D, we simply just added our 2 unit vectors for I, our 2 unit vectors for j, and our 2 unit vectors for k. In 3D, we're doing the exact same thing. Sorry, we didn't do k for for our 2D. For 3D, we're doing the exact same thing, except now we have k involved here as well. Okay, so we're just adding k, that's all. Similarly, how we would look at a line defined by 2 points. Let's say we have point A here, defined by x1, y1, z1, and point B here. We can connect those into a vector, which would be AB. We'll call it AB. And then we can move the tail of that vector to the origin and define that vector by simply finding the difference in the coordinates, right? Always our final or our coordinate at the tip minus our coordinate at the tail. So it would be x2 minus x1, y2 minus y1, and z2 minus z1. So in this case, we're just adding that third coordinate here with z's. So finding the difference in the coordinates actually does. So like the vector, like this vector here, this red one, is the exact same as that vector there. They're no different. One has just been translated to a different location. And to figure out what this point here is, right? Because it's OP and O is just 0, 0, 0. That's our origin. But to figure out where that point P is, that's what finding the difference actually does, right? So you can think of it as finding the difference between their heights. So you can see B is a little bit lower than A, and whatever we get for that value in that height, that's where we're going to place P from the origin, that little bit lower. And however farther away it is in this direction, right, which would be the difference between those coordinates, right, that's what we would, that's where we would place that y coordinate for P. And the same thing with z. I'm just terrible at drawing in 3 dimensions here, but there would be another one for z as well. Does that make sense? And lastly, another thing we can do is sort of the Pythagorean theorem, which is what we did before to find the magnitude of this vector. So let's say we have AB or OP, right? And we know its coordinates to be A, B, and C, right? So we can actually find the length of that vector by doing the square root of A squared plus B squared and now plus C squared. Of course, if we don't know OP and we just know A and B, we can do this as well, which is what we do to actually find OP anyways. So you can do it in 1 step or you can do it in 2 steps. Okay, so let's go over some example problems and we'll see how we're going to do. Start with number 1. So number 1 says, given A, and it's giving it in unit vectors, so minus I plus 2j plus k. And then we have similarly vector B and vector C. We have to find each of the following. So this is just collecting like terms. So for part A, we have 2a, so I'll just write it as 2 times a, which is minus I plus 2j plus k, minus b, so I'm going to make sure I put a bracket there because that negative needs to go into all the terms. B is 2j minus 3k, and I'm running out of room. I'll just go down here, plus c, and c is just I minus 3j plus 2k. So what we're just doing here is collecting all of our unit vectors for I and adding them together. Right? So here we have negative 2i. We don't have any i's here. Plus I. So that just gives us negative I. Here we have 4j, negative 2j, and over here we have negative 3j. So that just gives us negative j. And here we have k and then a double negative. So k plus 3k plus 2k Oh, this is 2k. So in total, 2 plus 3 plus 2 gives us plus 7k. Right? And if we wanted to, or if we were asked to, we can write that as a coordinate. -1, and 7. All right, so I want you guys to try take a minute and answer part B, and then we'll take it up. So in example 2, it says we have A at that coordinate and B at this coordinate, and they are in our cube. That means 3D. Determine each of the following. So OA. So a vector going from the origin to A, and we need to find its magnitude. Well, to find the magnitude, all we're going to have to do is that sort of 3D Pythagorean theorem. So the magnitude of OA. And we already know the coordinate from OA because it would be x2 minus x1, which is 7 minus 0, because we know our coordinates for O. That's the origin. So we can just do the square root of, we have 7 squared plus -11 squared plus 13 squared. And we'll get something that's approximately equal to 18.4. We can do the same thing for OB. And just take the square root, but then for B's coordinates, which would be 4 squared plus -7 squared plus 25 squared, and we'll get something that is approximately equal to 26.3. So that part's not too bad. But then in part C, we have to find the vector AB. So to do that, and I'm going to just go over to the side here because I won't have enough room. But for the vector AB, that's when we need to start doing the x2 minus x1. And an easier way to think of it is you're doing the coordinate for B. So let me just write it like this. Maybe this is easier to visualize. The x coordinate for B minus the A coordinate, the x coordinate for A. And then we have the y coordinate for B minus the y coordinate for A. And then we have the z coordinate for B minus the z coordinate for A. All right, so let's put in our numbers. So we have 4 minus 7. And minus 7, subtract -11, and 25 minus 13. And that gives us what AB is, -3, 4, and 12. Right? And you can draw that vector if you wanted to with the tail at the origin and the tip at those coordinates for x, y, and z. And then to find the magnitude, again, our 3D Pythagorean theorem, we'll take the square root of -3 squared plus 4 squared plus 12 squared. And this one works out nicely. It's equal to 13. Now for our last example, let's sort of remember that when we did 2D vectors, we said that some vector which has a scalar multiple of it is collinear with U, meaning collinear means that one is right on top of the other one. Okay, they're not only parallel, but they're right on top of each other. Okay, so part A says find the value of A such that this vector 1, 2, 3 and this one 2a6 are collinear. So for those to be collinear, what we need to have is this vector 1, 2, 3 needs to be some scalar multiple, let's call k, where k is a scalar, times by 2a and 6. Now this pattern is probably pretty easy to figure out. 1, 2, 3, 2, 6. I think we can easily see that a would have to be 4. Okay, part B is a little bit more tricky. Let me just scroll down. I'm going to use some space down here to do part B. So for part B, what we need is this vector, -2, b, and 7. If it's collinear to the other vector, then we need some scalar multiple. It must be equal to some scalar multiple times that other vector, c, 6, and 21. Now, if you can see just by looking at it what k would need to be in there for what b and z are, great. But let's imagine we couldn't. How would we actually solve this? Well, we can actually write 3 equations. The first one would be for x component, where -2 is equal to kc. The second one would be for y, where we would have b equal to 6k. And the third one, we would have 7 equal to 21k. So right away, you can look at equation 3 and say, oh, I can figure out what k is there. And k is going to be 1/3. Well, if k is 1/3, then I could go back to equation 2 and say, well, b is going to be 6 times k, where k is 1/3. So b is going to be 2. And then we can also go back to equation 1 to say, okay, -2 is going to equal to k, which is 1/3, times c. So multiply both sides by 3, and we'll get c equal to -6. So if b equals 2 and c equals -6, then those two vectors are collinear.